Hello dear friends, I am Keramettin Gutlu, and in this video I am going to do my homework about algorithm analysis in Java. We have some examples here and we will see the answer together. Let's start with our first example. As you see here, we had some codes, and let's check the time complexity of the following function. Let's start with this. As you see here, it is C1, it is C2, it is C3, we say, it is C4 and C5. Let's check their times. As you see, it's constant and we say 1. As you see here, I start with 0 and it says I small than n, and it's going to start with 0 and increasing one by one until reach the n, and we say it is n time it will work here, and this if function will work like this for function n times, and this function also work n times here, and result is 1. Let's make it. Let's find total cost here. C1 plus C2n plus C3n plus C4n plus C5. Let's make together the n's here, and C2 plus C3 plus C4, and we have C1 and C5 here. We can make it easier. This equals, like we say, a times n plus b. It's look like that, and we have some rules here. We can ignore a multiplicative constant here. As you see, if an algorithm is 5 times n cube, it also says n time n cube. We can ignore this value and a here, and our O notation will be n. Let's go to our second example here. As you see here, we have n times n here, and it will start from 0 to n times n, and O notation will be n times n equals to n square. As you see here, it's like the first example, but it is increasing 40. Let's make it. And we will divide by 40, and as you see here, we set multi-constant, and we can ignore the low order terms here. You can see that we ignore these two items here, and it will make it easier, our algorithms, and it will equals also n square. Let's continue third example here. It will seem like the other example, but we will divide this function by n because it's increasing by n. If we make it here, as you see, it's going like that, and it will equals to n. Let's continue with the other example here. Now our I start with 10 and increasing by 2 here. Let's write and time ends negative 10 goes here, and it will divide by 3, and also it will divide by 2, and as you see here, these examples we will ignore the constant variables here. They are all going and we don't need them, we just need n's here, and it will equals to n square. As you see here in this example, this function is constant, and we say, as you see here, if our function is constant, we use 1, just 1. Let's continue with our new example. As you see here, our I start with 1 and it's increasing 2 multiple times. Let's make it's starting with 2, and if our I is 2, we will multiple time with 2, and it will goes like that. 2, 4, 6, and 6, 8, and 16, and as you see here in this example, it's growing like logarithmic. You can see here, if our requirement for logarithmic algorithm increases says, and our own notation will be logarithmic function. Let's continue with other example here. As you see here, I equals to n, it says, and our initial value can't start with n, and there is no time complexity, we can say. As you see here, we have inner loop here, second loop. Let's check first loop for loop. It is starting with 0 and it goes until the n, I equals to n, and it will check it, it will work n times here, and our inner loop is start with m and j goes to 40, and it decreases by 4 here, and it will make it m times, and our own notation equals to n times m here. In this example, let's check the first loop here. It starts with 1 and it goes until the n, and it's increasing 5 times here. In this example, as you see, we said that it is a logarithmic function, and it is also a logarithmic function, logarithm n. As you see here, it is the inner loop, it's the same here, this function are the same, and it will also work n times, and you can say that all logarithm n times m. Let's continue with other function here. As you see here, if our n equals to 0, it will return 1, it is constant. If our n equals to 1, it will return x as also constant, we can say. But if our n is divided by 2 and our our function is equals to 0, it means that our n is even and equals to even. It will return x times x and divided by 2. If it is odd, if our n is odd number, it will turn x times x here, and it's also n over 2. It's also like, as you see here, we said that if it is going like these functions, they are same things, they are logarithmic functions, and we can say that it's also logarithmic function, and our big O notation will be logarithm n. We have a new example here. It says what is the time complex of Fibonacci function. We know that Fibonacci function goes like 1, 0, 1 plus 1, 1, 1 plus 1, 2, 1 plus 2, 3, 3 plus 2, 5, and 5 plus 3, 8, and it goes like this. Now let's check our function here. If our n is smaller or equals to 2, it will return 1, and if not, it will return n minus 1 plus n minus 2. Our recursive will be n x and n minus 2 r2 plus constant. Now I want to make a tree here. It will start with n, and it will divide n minus 1 and n minus 2. This also will be right, n minus 3, 2 n minus 3, and it will be n minus 3 and n minus 4, and it also goes like n minus 3 and n minus 4, and it will goes n minus 4 and n minus 5. They are the same, as you see here, n minus 4, n minus 5, and this will be going to n, let's calculate, n minus 5 and minus 6. If we say that it is c times, it will be two times c, because there are 1, 2 here, 1, 2, 3, and 4 operations here, and it will be 2 times c, and as you see here, 1, 2, 3, 4, 5, 6, 7, 8. But it will be, of course, not 8. It's going to be 4 times c, and we can say that it's equals to 2 square times c, and as you see here, it's also, we can say that 2 over 0 minus c. As you see here, it is increasing one by one in each step, and we can say that it's like going like 2 over n minus 1 plus c. And if you remember, we said that we don't need to constant variables here, and it's going to see here our recurrence is upper bounded by that, and if it is upper bounded, we say that it's weak O notation. And now let's continue with the last example, faster computer or algorithm. Suppose we have a fast computer that is 10 times faster than a slow computer. We have problem with two different solutions. Fast algorithm takes n time, slow algorithm takes 2 square time. Which is faster, slow algorithm running on fast computer or fast algorithm running on slow computer? Let's say our fast computer takes s time and slow computer takes 10 seconds. Slow algorithm running on fast computer. It means that slow algorithm is n square time and fast computer as fast algorithm running on slow computer, or n time 10s. As you see, we can ignore a multiplicative constant in algorithms, so we don't need these constant variables here, and it means that it doesn't matter which computer are we using, fast computer or slow computer. It doesn't matter in algorithms. It is just about the algorithms times, what time they are taking. In this example, of course, fast algorithm in running on slow computer will be work faster than slow algorithm, because ON is takes less time than slow algorithm. It's going like 1, 2, 3, 4, 5, but it goes 1, 4, 9, 16, 25. As you see, fast algorithm running on slow computer is faster than slow algorithm on fast computer. It doesn't matter which computer we are using. And thank you for listening to me. That's all for today. Goodbye.